Welcome all. In this lecture, we will study about fatigue testing. We will know about fatigue and we will also see that how we can perform the fatigue testing. In order to understand the fatigue, we will take the simplest example of a paper clip. If we want to break this paper clip into two parts, then firstly we will straighten this wire, and after the straightening of this wire, if we apply the tensile loading from both of the on both of the ends of this paper clip, or you if you will pull the paper this wire of the paper clip from both the ends, then you will observe that it is very difficult to break this paper clip. But if you will hold one end of the paper clip in your one hand firmly, and on the other end you will apply it, you will move it in the to and fro directions, then you will observe that it is very easy to break this paper clip. Another example we can take of this cycle crank. So cycle crank is the part which is attached to the pedal as well as to the this sprocket. So when the rider is riding the bicycle, so each time the rider pushes this pedal, one load cycle is completed. So during that load cycle, at one instant of time, the load is applied by the rider, and during the remaining part of the this cycle, the crank is free from the load. So as after using the this bicycle for months and years, then it generally fails, and this failing occurs due to the fatigue loading. So fatigue loading is the degradation of mechanical properties, which in turn leads to the failure of material or the component when it is subjected to cyclic loading. So actually fatigue failure is estimated to comprise 90% of metallic failures. So all the failures which occurs in metallic components, 90% of them are composed of fatigue. So if we have to define fatigue, then we can define it as the failure of a component at much lower value of load when it is subjected to cyclic or alternate loads. So here the much lower value of load is compared with the maximum value of the load with which the part can sustain when it is subjected to static loading. And cyclic or alternate loads are the loads which change either direction or amplitude or both in a repetitive manner. So when a component is subjected to cyclic loads over a long period of time, then the component fails at a much lower value of load when it is compared with the value at which it will fail under the static loading. Another common examples of fatigue failure which we can see around us are shown here in the pictures. So first example is of the gear. So gears are used in power transmission. So these are mounted over the shaft. So when if you have to impart more power, then the gear rotates at different speeds, and if you have to impart lower power, then these gears rotate at another speed. So as for the power transmission, gears meshes with one another. So at high powers and low powers, the rate at which these gears revolve that differ is, so during meshing they apply force over one another, and this force actually leads to the fatigue loading of these gears. So here you can see the gears has been worn out, and this is due to the fatigue loading. In this diagram you can see that the hull of the ship has been broken down into two parts, and this occurs because of the fatigue loading, because when the ship moves over the sea, so the sea waves applies tensile and compressive forces over this hull of the ship, and of during long usage it generally fails due to the fatigue loading. So here you can see this the complete failure of this huge ship. So these are the wheels of the train. So these are also subjected to fatigue loading. If you consider any point on this wheel, so when that point comes in contact uh, with this platform, then it is subjected to compressive loading, and when it completes the cycle, then in the remaining part of the cycle it is free from that loading. So this is completed in millions of time during one side journey of train. So this also leads to the fatigue failure. This is the example of a crank shaft which is on which the pistons are mounted. So this is also shown here in the failed positions, and this is due to the fatigue loading. So these giant wheels you might have seen in the amusement park, these should be designed in order to these should be designed by considering the fatigue loading. So another example of fatigue loading is the aircraft. So when aircraft moves, when aircraft flies, so these wings of the aircraft are subjected to different uh, pressures by the air at different altitudes. So this produces fatigue loading in the wings of the aircraft. So automobiles on roads are also subjected to fatigue loading. Bridges, so on bridge the traffic generally varies at different time or different points of time. So uh, the traffic also induces fatigue loading in the wind. So turbines, when subjected to cyclic temperature conditions, means uh, when the turbines, suppose the steam turbines if you are using, so if the temperature of the steam varies, so the cyclic temperature conditions are produced, and this in turn produces cyclic thermal stresses. So that also introduces the fatigue loading. So process of progressive localized permanent structural change which occurs in a material when it is subjected to fluctuating stresses and strains at some points, such that these points may culminate in cracks or complete fracture after a sufficient number of fluctuations. So in this way we can define the fatigue testing, that the load which is producing fluctuating stresses and strain produces progressive localized permanent structural change, or you can say that produces plastic deformation, and that plastic deformation grows over a period of time leading to the failure of the component. So the processes of fatigue failure consist of three stages. So first stage is composed of the initial fatigue damage, in which the crack nucleation and crack initiation takes place. And in the second step, when the crack has nucleated, then the crack propagation take place, means crack starts to grow during the load cycles, and after that the final fracture or sudden fracture of the remaining cross sections occurs. So in this way, with the crack nucleation and propagation, the failure of the component occurs. How we can apply the cyclic loading? So cyclic loading we can apply with the help of dynamic UTM. So this is the schematic diagram of a UTM, which is universal testing machine. So in this machine we can perform a number of tests, including tension test, compression test, bending test, and this cyclic loading we can also perform. So here this bottom grip is fixed. In between these two grips the our specimen is placed. So one of the grips, which is the bottom grip, is fixed, while the top grip will can be moved in the upward and downward direction, which in turn applies the cyclic load. So this is the actual dynamic machine. So this is a hydraulic dynamic machine. So this is the bottom grip, which is fixed, and the top grip can be moved in the upward and downward directions according to your load applications, and the sample is placed in between these two grips. So either tensile and or compressive cyclic load you can apply. So this is the typical loading cycle, where this shows the maximum amplitude, and the this point, which is the bottom point, shows the minimum amplitude of the stress, and the distance between the two crust or the two trough is known as the one stress cycle. The If you move from the zero positions, or the point at which the stress is zero, then in the topward direction shows that the load is tensile in nature, means the effect of the load is to increase the length of the specimen, and in the bottom directions the load is compressive in nature. So it is not mandatory that you will apply only the sinusoidal load. You can also apply a triangular load. You can also apply a square wave. So in this in these waves, you can see the time period in which you apply the load, that actually varies. Likewise, in square wave, you can also hold the load for some amount of time. And here this is the zero position, and from the zero position in the upward direction, the load is tensile in nature. Means from here, from zero positions, if you're moving in the upward direction, then this load is tensile in nature. Then the magnitude of the load is decreasing, and after that it is changing into the compressive load. So here is the random stress cycle, where the amplitude of the load as well as the direction of the load is changing. So in diagrams A, B and C, the amplitude of the load was constant in the tensile and in the compressive cycles. The only change was the direction. So here in the random stress cycle, the amplitude as well as the direction is changing. There are some parameters which we need to find out from the stress cycle. So likewise, the maximum stress is denoted by sigma max, whereas the minimum stress is denoted by the sigma minimum. So this is the typical cyclic loading, which is shown in the form of a sinusoidal load. Here, this type of loading explains all the points which will be discussed here. So this load either can start from the zero positions, or it can start from at any point above the zero stress value. So mean stress, if you have to calculate, then it is equal to the sigma max plus sigma minimum divided by 2, means the maximum tensile load and the maximum compressive load divided by 2 give rise to the mean stress. Then we have stress amplitude. That stress amplitude is the difference in the maximum load and the minimum load divided by 2. And range of stress is the difference between the maximum load and the minimum load. Whereas the stress ratio R, this is the ratio of the sigma minimum, which is the compressive maximum value of the compressive load, divided by sigma maximum, which is the maximum value of the tensile load. So here, the as we have discussed, that above the zero stress value, in the positive direction we have tensile load, and in the negative direction we have compressive load. So this first cycle shows the alternating load, where the load is changing its direction. So the load is tensile as well as compressive in nature, but the magnitude of the load is different in both the cycles. So here the stress ratio is less than 0, whereas in the second case we have alternating load, where the maximum stress cycle in the tensile case as well as in the compressive case, these are equal in nature. So means sigma minimum is equal to sigma max. So here the stress ratio is equal to 1. Another one, we have pulsating load, means in this case the load is changing, means at one time it is having the zero stress value, at the other time it is having the maximum stress value. So here magnitude is changing, but the direction of the load is not changing, means direction, the load is not moving towards the compressive side. So another one, we have static load, where R is equal to 1. So these type of loads we can apply, where the positive side refers to the tensile stress and the negative side refers to the compressive stress. Then we have the SN curve, where signifies the stress and the N stands for the number of cycles of failure. So suppose you are testing the material at some higher stress value, and after that higher stress value, at that higher stress value you are calculating the number of cycles at which the failure of the component takes place. Then you will get 1 point. Then you lower the stress value and you calculate the number of cycles at which the failure of the component takes place. So you will get another point. So in this way you will plot the number of points and you will get a curve which is SN curve. So in SN curve, you can see that a point will come after that this curve the curve turns into a straight line. So that straight line or the stress corresponding to straight line is known as the fatigue limit. Means at below this stress value, no matter how many load cycles you apply, the component will not fail. And if you increase the magnitude of the load or magnitude of the stress, then the failure of the component can take place at a lower stress value. Sorry, the failure of the component will take place at the lower number of cycles. So this is the importance of the SN curve. You can plot it for any material and you can find out the fatigue limit. Means this is the safe limit within which if you will work, if you will apply the stress, then your component will have uh, infinite number of cycles your component can sustain. So this was all about fatigue loading. Thank you.